In this lesson, we will determine the time of death through bug analysis. In order to do that, we need two things. Number one, temperature data. All insects are cold-blooded creatures, and they rely on their temperature of their environment to increase their body heat. Number two, we also need to identify the species. If we can correctly identify the species, we can then determine what stage they are in their life cycle to get accurate readings. In this video, we will work through a case study, and in the case study, we will use the following 5 steps to help determine the time of death. Here we go. Case 2, the man in the woods. In a small rural town during the summer of 2003, a body of a white male approximately 40 years of age was found in a nearby wooded area. An investigation revealed this individual died from a single gunshot wound to the head. The victim had additional injuries to his abdomen and right knee. While no flies were collected at the crime scene, samples of maggots were collected and preserved from the victim's abdomen, knee, and skull during the autopsy at the medical examiner office. The maggots were identified as the mature larvae of 2 fly species, the secondary screwworm fly and the hairy maggot fly. Complete the table to determine the earliest and latest dates that the person could have died. On the back of this case study, what you will notice are 3 data tables. Table 5 gives us the date, 2 weeks prior, gives us the temperature, and we'll have to solve for all the information right here. Table 6 gives us the developmental data for the secondary screwworm fly, and Table 7 gives us the data for the hairy maggot fly. So to determine the time of death, the first thing we're going to do is calculate the mean average. In order to do that, it's simply the max plus the min divided by 2. In Table 5 here, what you'll notice, starting from the top, 93 plus 70 gives me 163 divided by 2, and I get 81.5. Again, it's max 91 plus min 74 divided by 2, and that gives me 82.5. And I'm just going to go ahead and fill in the rest. Step 1 is complete, and that's what you should see for that mean degrees Fahrenheit column. The next step, what we're simply going to do is convert Fahrenheit to degrees Celsius. And most importantly, we're going to round to the tenths place. So here's my equation. The mean degree Fahrenheit minus 32 times 0.556, and that will give me my mean degrees Celsius. So in the next column, I'm going to take 81.5 minus 32 times 0.556, and that gives me 27.522. I'm going to round to the tenths place, 27.5. Again, 82.5 minus 32 times 0.556, 28.1. I'm just going to go ahead and fill in the rest. And that's what you get for the next column for mean degrees Celsius. The third step is to calculate the base temperature, degree day minus B6. Now remember, all insects are cold-blooded, so temperature plays a role in growth and development. The base temperature is what we consider the lowest temperature where metabolic processes can result in gain. So therefore, we have this equation that is mean degrees Celsius minus 6, which is going to equal our degree day B6. The degree day is a way for us to measure insect growth and development in response to daily temperature. How we calculate this in the next column is we simply take 27.5 minus 6, and I get 21.5. Again, we're going to take our mean degrees Celsius, 28.1, and we're going to simply subtract it by 6, 22.1. And I'm just going to fill in the rest. And that's what you should get for that column. In step 4, we will calculate the ADD, which is what we call the accumulated degree day. Now, this predicts when the different stages of insect development will occur. And in order to do this, it will determine the amount of heat that's going to be needed. Here are the steps that we will use for the next column. By transferring the current BB6 temperature to the add column, we can then add that current temperature to the previous add number, and then we can repeat that until the whole column is completed. So basically what I like to say here is we take the degrees and we basically start converting these into hours. Here's what this looks like. 21.5 goes into the add column as 21.5 hours. What we're going to do now is we're going to take 21.5 and we're going to add that to 22.1, and we're going to get 43.6. Again, we'll repeat that. We'll take 43.6, we'll add 19 to it, and we'll get our next answer of 62.6. I'll just go ahead and fill in the rest. And that's what you should get for the add column. Now the last step is the trickiest step. In step 5, what we're going to do is determine the colonization. This will give us our final answer, which is the estimation of the time of death. And what we will do is we'll follow these steps here. The first one says use the DDB6 column to determine the temperature column in the developmental data. So for example, this is my degree day B6, and I'm going to use this to determine which one of these 3 columns I'm going to use. If I could average these out, I noticed that this might average around 21. So therefore, this will be the middle column that I'm using. I will not be using either one of those 2 columns. Again, temperature plays a very important role for insects. Number 2, I will use the life stage given to determine the minimum and maximum hours for being in that stage. On the front of this case study, we noticed that both larvae were 3rd instars. Okay, so basically maggots. Because it was a 3rd instar, that meant that this insect could be alive for 72 to 171 hours. Notice at 172 they are in their pupal stage, which is why I stopped 1 hour shy of that to 171. The last part says use the add column to determine the minimum and maximum days of death. So basically what I'm going to do is take this range and fit it into my hours of estimated time here for the first fly. So the Cochleomya macellaria fly, If I was a third instar larvae growing at a temperature of about roughly 21 degrees, I could be alive between 72 to 171 hours. In my add column here, notice that at 83, this would be my minimum amount of time that I could be alive for my Cochlomya macellaria fly, right? Notice this puts me over. To get the max over here, it should be under. So if I'm going to fit 171 in this range, it would fit at 163. This would be the maximum amount of hours that this fly could be alive for. Let me repeat that for the next fly. For the next fly, again, it was also a third instar. And the temperature column is still the same at 21. I'll X out those two. Third instar, which means this fly could be alive for 92 to 128 hours. Therefore, I'm going to take this number, this range, and fit it in my range up here. 92 without going over would fit at 100.4, a minimum for this fly. And at 128, my max would be 141.5 without going under. Now I've solved for the case. To determine the time of death, for the first fly, the secondary screwworm, the time of death gives me a range of from 7:7 to 7:11. That's a pretty big range for someone being dead in the woods. The next fly gives me a better range from 7:8 to 7:10. I have now completed this case study, and I could make the assumption that this man who was found in the woods was dead anytime between the following dates that I have below.